In this lesson, we will go over three types of tangency problems. The first is the most standard and the simplest case. When a curve is given by a graph of a function, the typical problem looks kind of like this. When a curve is given by a graph of a function y equals f of x at specified x-coordinate value x equals x naught, we can find out the equation of the tangent line using this step-by-step process. Step 1, y-coordinate. You can do that by plugging x equals x naught in the definition of the function. Step 2, derivative. Step 3, slope. Step 4, now that you found out the slope in step 3, and then x naught is already given from the problem a priori, and y naught was found in step 1. So we have all the ingredients to put everything into the slope point equation of the line. And then if you need to get slope-intercept equation, you can take a little bit of algebraic manipulation to expand it further. This four-step process can be summarized in a single line like this. However, unless you are a very experienced student, I would rather advise you to go over this four-step process rather than trying to do this all at the same time. The reason is that I ended up with so many mistakes by students that otherwise they wouldn't make. Let's go over to an example problem. I wrote several problems here. Let's go over to the first problem, which is the easiest. As usual, I'll do only the easier one and then leave more complicated problems to the students. Here we go. Let's go over to the first step. Now that we know the x naught is 3 given by this problem, let's find out y naught. Let's plug in x equals to 3. So this is f of 3, and plugging x equals to 3 to this equation, we'll have something like this. This is not difficult to calculate. 3 squared is 9, so I have 9 halves, and then square root of 9 is actually 3, so we have 9 halves minus 3. This will be 3 halves. Okay, step 1 is done. Let's find out the derivative. Step 2 is the derivative. The first term is easy, calculating the derivative of x squared times 1/2 x squared. Wait a minute, looks like a little bit of simplification is in order because the second term is not given in the power form. The first term is okay, that's perfect. Now square root of 3 times x inside the square root, that's the same as square root of 3 times square root of x. Further simplification yields square root of 3 times x to the 1/2 power. Now we are ready to apply the power rule. Alright, let's find out the derivative of the first function. It's just x, it's easy to see. Let's align the equality. Okay, the next 1/2 comes out and we have square root of 3 over 2 times x to the negative 1/2 power. This is perfectly fine, but let's take a little bit of algebraic manipulation here, because negative 1/2 power is equivalent to square root in denominator. The final step is not really necessary because today's calculators can handle, well, negative fractional power just as easily as traditional notation. Now that we found out the derivative, let's find out the slope. Let's plug in x equals to 3, so 3 minus square root of 3 over 2 square root of 3 So immediately we get simplification. 3 minus 1/2. What do we have? We have 5/2. Okay, there goes step 3. Now that we have the slope, y-coordinate, and then the x-coordinate, we are ready to put everything into the slope point equation of the line. 5/2 x minus 3 plus 3/2. This is an equation of the tangent line we are looking for. Excuse me, this is an equation of the tangent line which is correct. However, this is not the equation that we are looking for. The problem said the slope-intercept equation. Alright, let's take a little bit more algebraic manipulation. Oops. 5x minus 15/2 plus 3/2. So what do we have? 5/2 x minus 6. Here we go. So we have y equals to 5/2 x minus 6 as the final answer. This concludes this example problem, part A. Let me make a little bit of additional comment here, because I've seen so many students making this mistake over the years. Well, they remembered slope point equation, and then they remembered the derivatives gives a slope. So they do something like this, assuming they did calculate derivative correctly. Kind of like this. Of course, students making this kind of mistake usually do not use parentheses correctly, so that's typical. However, even if you use parentheses correctly to get a derivative function over here, still this is not a correct answer. What we need is an equation of the line, which means the right-hand side has to be a linear function. But what we have here, we have two complicated x. This is quadratic, and then square root of x. Oh, this is too complicated. This y equals to, well, whatever this expression is not a line. It's going to be another curve. The reason this kind of mistake took place is the students did not understand the difference between the derivative function and then the derivative. The derivative is a number and it's a slope of a tangent line. The derivative function, on the other hand, is a function that gives you the derivative value when you plug in appropriate x values. For varying x values, it gives you a curve. So f prime of x is not the right choice for this part over here. What we need is m, the slope. So step 3 is absolutely necessary, and step 4 must be a lot simpler than this kind of thing we just had before. Alright, now that we completed the solution, let's verify a solution through Mathematicas program. Here it is. Please note that in this program we are using the very same function, 1/2 x squared minus square root of 3x, the same, and then it yielded the blue curve, the original, and then the red line, the tangent line, and not surprisingly we have tangency touching point at x equal to 3. And one more thing, here in this Mathematicas program, f prime of x, x minus x naught plus f of x naught is the same as this equation here. Not surprisingly, we have correct visualization. The other problems are kind of like this too. I have wrote many more problems here, but except for a little bit more complicated functions, the idea is exactly the same. Same step-by-step process. Y-coordinate, derivative, slope, and then the equation of the line. The derivative computation may be a little bit more complicated. You may have to use product rule, kind of like this, or quotient rule. And each problem actually comes with visualization through Mathematica. However, I'm not going to open these cells and show you the visualizations because it'll give away the answers. These problems are left to the students.